I'm an honors student with the University of Johannesburg. I'm presenting my honors year project, and my mentor is Mr. Maluleka. The name of our solution is called Automated UI. So I'm just going to take you through the brief presentation of what we have and what the solution entails. So the problem that we're trying to solve effectively is taking wireframes that are hand-drawn in and interpret them into HTML pages that can be used for prototyping and also generating user interfaces for the final product. So the main key problems that we are solving is through the SDLC, where designing user interfaces requires prototyping and also a lot of back and forth process with regards to presenting to technical and non-technical audiences. So the problem that we are solving, or the benefits of implementing this solution, is to eradicate or to reduce the wasted resources in terms of humans and also money, and also taking out the repetitive tasks in the SDLC as we know it. Proposed solution that we have in hand is a solution that will be able to interpret hand-drawn interfaces into HTML pages. The solution must be able to understand different wireframe components such as buttons, labels, text boxes, radio buttons, and so forth. So the benefits of us doing this project is that we're going to eliminate a lot of costs and a lot of time that is spent during the SDLC to design and prototype and also implement the final user interface of our solutions. And also we eliminating repetitive tasks, which means we are going to save a lot of time, in a sense of developers will not need to now implement or re-implement what was implemented in the prototype. They'll just need to get a package from our user interface UX team that will give them a package with basic HTML pages or layout, so to say. So the solution pipeline, we have taken the machine learning approach, where our input will be a hand-drawn UI design, and our ultimate output would be an HTML page that can be used on our final product. On our pre-processing step, as the machine learning process pipeline actually requires, we are taking a complex image that can be seen on the left and taking out little bits of components from the particular image that we have. So here you can see that we have extracted a drop down, a button, and an image. So in our approach for pre-processing, we are grayscaling the images, so removing color noises. Some backgrounds have blue background, some have, like this one, kind of orange to brownish background. So we're removing that by grayscaling the images, and also we're changing the images dimensions to a set dimension of whatever configuration that we have, so that we eliminate the potential or possibility of image dimensions affecting the accuracy of our model. Our features, which is the next step, is hog features. They depend on distance. So we're using a KNN, and we're also using hog feature extraction or hog features. They heavily rely on the dimension of the image. So hog features, if you look at it, it's the change in gradient on the Y plane and also on the X plane given a particular image. So when we look at hog features, what we'll input into our model is typical images that you can see on the left, and based on that, say for example, if we were to choose a button, we would have an X gradient changing heavily on the Y plane, where we see a lot of noise on the Y plane rather than on the X plane. And when we choose our X gradient, we'll see that there's a lot of change on the Y, or the white dominating color of white on the X line more than on the Y plane. So when we do that, what we then do is we dissect the image into multiple blocks that give us hog representation of those dimensions. Then after that, from our hog features, what we then do is we feed our hog features into a KNN, k-nearest neighbors classifier that basically calculates the Euclidean distance. So as mentioned, the KNN classifier uses Euclidean distance to calculate differences between different classes. So in our sense, it would be between an image versus a button, or a button versus a text box, or whatever the case might be, to categorically predict different components. So what we then do on our training level is that we save different models, and according to their accuracy rates, then once we've done that, we use them on our next process, which is prediction. On our prediction, we then load our KNN models that have already been trained. We take an image that has complex elements, and then we predict different elements on the particular image. Once we've done that, we then generate HTML pages that can be used for prototyping and also the final product that we require. Then on our results set, what we have is we tried the KNN hog feature combination. It gave us between 67% and 87.9% accuracy. Then we tried our KNN and LBP linear binary pattern features, which gave us 46% to 54% accuracy. Then we tried the multi-class SVM and LBP feature combination that gave us between 42% and 49% accuracy. Therefore, we decided to run with our model combination of KNN and hog features. The issues that we encountered is that the initial implementation of the KNN was inaccurate, and therefore gave us inaccurate results, in the sense that we were summing up the different hog features of different blocks instead of analyzing them separately. Then what we also came across was that the sliding window approach created a lot of images, or had to analyze a lot of image blocks, and that charged a lot of computational resources. Then we went for an edge-based approach, where now we get different edges on the image, and based on that we take that as points of interest and analyze around that particular points. That is a promising approach. It has not worked fully, but then we believe that it will work effectively on future iterations of the system. In terms of the demo, I'll just jump into the demo itself. In terms of the demo, what we have on our project is that we have pre-processing step as explained, feature extraction, which uses hog features or extracts hog features. We have model training. We have the compact analysis of an image that's that has multiple components, and here we give it a folder that has different components and generate HTML from that. So the pre-processing step, basically what you can do is resize your images, grayscale your images. Then once you do that, it will give you an output of the different images. So this process is currently pre-processing around 1,200 images that we have as our input images. Then the output would typically be something along this line, which is the original image with the noise of the background, which is kind of brownish, taken out to produce this pre-processed image that's resized to an 80 by 40 according to our configuration. Then on our next step, what we then do is we extract features. When we extract features, we are extracting effectively our hog features for those inputted or pre-processed images. Then our output basically is, as explained on the slides, we would get the gradients of the different images. Here I'm showing a button as an example, and this would typically be a hog histogram of a particular block in the image. Then on our model training, basically what we then do is we train our model, we specify the size. So the size is dependent on the input. So if, let's say for example, we're inputting 1,000 images and we choose 0.2, which is 20% of the particular input, then we'd have 200 images or features inputs that are being used for training purposes of our model. And when we train our model, what we effectively get is what is called a confusion matrix that will tell us that there's, in terms of our training, on our true label we said the image, the particular image that was inputted was a button, however it predicted a video. We'd also see, sorry about that, so here you'd see the actual text input that we had there's 4 of them that were predicted as drop downs. So our model accuracy for this particular model is sitting at 87%, which means all those that were inaccurate are actually plotted in this particular confusion matrix. Then on our model prediction, what we then do is the process of predicting different components on the same image is currently not fully functional, in a sense that there's a lot of computational resources that are required. But then what I'll then do is determine different components that are sitting in a folder, and based on that we'll now generate an HTML output. So this is our inputs. It's 2 labels, 2 images, 2 buttons, 2 drop downs, 2 check boxes, and we have 2 videos, and finally 2 input boxes. So what I'm going to do here is I'm just going to select that particular folder. Once I've selected the folder, the model will then predict all the elements that are in that folder. So it will give me a typical output that looks like this. Then on the output, what I can then do is generate an HTML. Once the HTML is generated, what I can then do is save it for later usage, say for example on the prototype, demonstrating the prototype, or also demonstrating or creating the final project itself. So our output typically looks like this based on our predictions. We have a label, we have 2 text boxes, we have another label here, we have a button, we have 2 text boxes, then we have a video and 2 check boxes and 2 other videos. What we then did was to allow users to actually manipulate the HTML that's generated on the fly. So when they delete the results from this particular set, what then happens is that all the components that they have decided not to have on their prototype will then be removed. Then based on that, you can generate HTML, save your HTML, and when you come to your output changes accordingly. So that's their I would say the overview of the project itself. Thank you very much for your time, and I'll be available for questioning should you contact me through email or any other medium of communication that I'm available on.